All right, so almost there with higher dimensional CFTs. So let me, as usual, recap a little bit where we stand. So we have arrived at this very attractive mathematical picture of what conformal field theory in general dimensions look like. We have seen that we should describe everything in terms of local operators and their correlation functions. And these local operators are labeled by so-called CFT data, which is the spectrum. So spectrum consists of scaling dimensions and spins, which arise by decomposing the Hilbert space on SD-1 into irreducible unitary representations of the conformal group, where these delta and rho can be thought of as labels of those representations. So that's one piece of CFT data, and the other piece of CFT data are the so-called three-point functions, or three-point structure constants, or structure constants of the OPE, which are the CIJKs, where for each triplet of conformal primary operators, there's some finite number of these three-point functions, where the number only depends on the spins. And we have seen some simple examples. Well, we have only seen one example of it, which is when the three spins are scalar, in which case there is only one number. And the reason why this data is enough is thanks to the OPE. So the OP, let me just write the OP in the most general form. The OP is a way to take two primary operators at two positions. So now I'm writing the most general thing, meaning that A runs from 1 to the dimension of this representation, and similar for B. And there's also going to be C. So we have seen that in principle, this can be written as an infinite sum. So firstly, we are summing over all of the representations. Then there is some coefficient, which is the same as the OP. Sorry. Okay, I need to sum also over the structure. So we need to sum over this alpha, which is some finite number of these structures. That's supposed to be the same number. Then we have a CIJK alpha. And then we continue below the line. We have some big differential operator, which depends on I, J, and K. It carries some indices, so it carries indices A, B, and C. So I'm writing it slightly more generally than I wrote it on the board last time, because I want to write the most general thing. And this differential operator only depends on the distance, or on the vector x1 minus x2, and the derivative with respect to x2. And it acts on the conformal primary operator OK with index C inserted at x2. Okay, so this is the most general form of the OPE for any spins. And this OP can be used inside correlation functions as long as we can find a sphere which surrounds the operators 1 and operator 2. Okay, so far so good. At the end of last lecture, we have said that this CFT data is actually constrained by associativity. So the first thing to say is that the CFT data can be used to compute any correlation function, because I can consider any correlation function and just use the OPE iteratively. And in particular, when we use the OP in a 4-point function, right? So in a 4-point function, we would have 4 operators: OI at x1, OJ at x2, OLD, let's say x4. Then using the OPE, we would arrive at sum over M and sum over these structures alpha. So now alpha runs from n I, j, k, and we have C CIJM, CKLM, the corresponding structure here, times an object, which is the conformal block, which depends on representations I, K, J, and L, on the representation M, and well, I suppose it also depends on the indices. So okay, it's kind of a big, nasty object, but the point is that okay, so this G is called a conformal block. And the conformal block is completely fixed by the symmetry, because this differential operator is completely fixed by symmetry, and once we put the OP in, then we end up with a 3-point function, which is also completely fixed by conformal symmetry. Okay. And then the idea was that the CFT data is not completely arbitrary, because we can do the OP in different ways. So we can either do the OP like that, so meaning that we first do the OP of OI, OJ, and then, another way of thinking about what I'm doing is that I'm doing two OPs. I'm doing an OP OI, OJ, and OK and OL, and then I'm computing a 2-point function. It's completely equivalent to what I'm saying. Or we can do the OP in the other way, which is the following picture. Okay, maybe let me write a sum. So we are summing over M. And here we are also summing over M. I, J, K, L. Okay. Yes, thank you. Sorry. Yes. It's I, J, and M. Okay, so schematically the equation looks like this, and in equations, now I'm going to stop writing all of these indices. Let's just imagine that everything is a scalar, but there is a very natural generalization of all of these equations to external non-scalars. So IJM, in that case there is no index alpha. So here it just depends on the delta I, delta J, delta K, and delta L. Delta M and rho M. X1, X2, X3, X4. So that's the left-hand side. And the right-hand side is obtained just by permuting whatever happens at 2 and whatever happens at 4. So I, L, M, C, J, K, M, and delta I, delta L, delta K, delta J, and still delta M, rho M, and X1, X4, X3, X2. Okay, and this is the conformal bootstrap equation in general dimension. And when I read you the quote by Polyakov, what Polyakov was trying to say is that this is some kind of an algebraic characterization of conformal field of fixed points of conformal field theories in general dimension. And the dream is that this condition is not only necessary but also sufficient. That if you can solve all of these equations, so if you can find all the solutions of all of these equations, then you're going to find all CFTs. And they're really, it's a very large set of equations, because I, J, K, and L are arbitrary, so IJKL range from 1 to infinity, or 0 to infinity. And also x1, x2, x3, x4 are some positions in RD. As we discussed yesterday during the Q&A, the equation doesn't really hold for arbitrary choice of x1, x2, x3, x4. You need to be careful. You need to make sure that both OPEs converge, but that's just a subset of measure 0 in the space of possible configurations. So for generic values of x1, x2, x3, x4, both sides converge, absolutely, and the equation holds. So there was a question, yes? Well, yeah, so let me just do it here. Because with spins there are various extra complications. So let's just look. Right. So if you think of it in this way, let's just look at on the left hand side of that equation. Right. So you could use OP on 1 and 2. So then you would have CIJM from the 1, 2 OPE. And then you can use then you can do the OP on 3 and 4, and you'll be summing over M prime, right? So you would have KL M prime times something complicated, but basically it's just you're going to end up with a 2-point function. There are some differential operators, but ultimately you have a 2-point function of OMX2, OM prime X4. Right? Do you agree? So this is how you doing the OP into, but this goes like, I mean, this is diagonal, right? We said that the 2-point functions of primary operators are proportional to the Kronecker delta. So this double sum collapses into a single sum. Yeah, thanks. That's a good point. Any other questions about this? About a general story? Okay, what did I want to say? Yeah, so you could of course ask, is it actually true that that the equation knows everything about the subject of CFTs? And we don't know, but there's some strong evidence that it knows a lot. So for example, people have applied it to 3-dimensional CFTs with Z2 symmetry, of which the most famous example is the critical 3D Ising model. And they found that for the critical 3-dimensional Ising model, the scaling dimensions delta sigma and delta epsilon are determined by this equation to I think like 7 or 8 decimal places. But okay, the process of actually getting there is very technical, very hard, because these conformal blocks are some complicated functions. You're trying to solve infinitely many equations in infinitely many variables, so it's not clear how to solve anything analytically. So what I want to do now is to basically take this complicated equation and try to kind of increase your intuition about what this equation does by looking at it in the simplest possible example. Okay, so we have this huge infinite set of equations, and let's just look at some subset of these equations. And the subset we are going to choose is when all 4 external operators are the same. So I, j, k, and l are all the same. And they correspond to scalar operators. So rho I is rho j, rho k is rho l. Of course, this follows from that, and it's just a trivial representation. So in other words, identical external scalars, because many of the features of the general story are already transparent in this case. So, yes. So external means the four leaves of this tree graph. So the external, the ones that we are inserting into the 4-point function, as opposed to the internal one, which is the one that we are summing over. And let me just drop the index I, because they're all external. I mean, they're all identical anyway. Okay, so we want to look at the 4-point function of four identical scalars, and the first order in business that we should do is to use conformal symmetry as much as possible. Of course, we could just kind of go through the steps that we did before in this particular case, but let's simplify our life a little bit, and let's first understand the consequence of conformal symmetry. So, there's an argument that I described during the last lecture why the 3-point function is completely fixed by sending 1 point to infinity, 1 point to the origin, and another point to an arbitrary third point. So let's think about what happens with the 4-point function. We can try to repeat the same thing. So let's say we use the inversion. So basically the question is, what are the parameters? What are kinematic parameters that the 4-point function depends on? And here's how to think about it. So we can use the inversion. Maybe let me write it bigger over here. So inversion, or special conformal transformation, if you wish. We can arrange x4 to go to infinity, and the 4-point function doesn't change. Then we can use translations to send x1 to the origin. And then we can try to work with x3 and use rotations, so all of these SOD rotations and scaling to send x3 to any point that we like. So rotations and dilatation. We can send x3 to the unit vector in the direction 1. So now x1, x3, x4 are on a line stretching between 0 and infinity. And we have x2 still, so x2 we haven't touched. And it would seem that we are done, but we are not quite done, because we are in some, just imagine we are in a 3-dimensional CFT, so we can still rotate around the axis connecting the origin and infinity, right? Because 1, 3, and 4 are on that axis, so we can use the rotations around this axis to bring x2 to any 2-dimensional plane. So we can still use rotations to bring x2 to the plane, let's call it 1, 2 plane, right? So the plane spanned by the unit vectors in the 1 and 2 direction, which means that the conformal invariant information in this 4-point function is captured by 2 coordinates, which are the 2-dimensional coordinates of x2 in this plane. Okay, well, and there's a nice way to parameterize these coordinates, which is called cross ratios. So cross ratios are the conformal invariants of 4 points. So 3 points have no non-trivial invariance, but 4 points do. And they are usually called U and V. And they take the following form. So this is U. Let me first write it. Now x14, let's say, x23 squared, x13 squared, x24 squared. Okay, so you see that they are both invariant, obviously invariant under translations because they just depend on differences of points. They are also obviously invariant under scaling because every point appears with the same weight. So, well, in fact, the only thing that you need is that the total weight upstairs and downstairs is 4. So it's also under scaling. Rotations also because it just depends on the norm of these vectors. So the only thing which is non-trivial is that it only depends. It's invariant under special conformal transformation. But for that, it's sufficient to check that it's invariant under inversions, right? So if it's invariant under inversions and everything else, then also special conformal transformations are okay. And so one thing that you do as an exercise, that an inversion, so inversion acts on points like that. So it sends xij squared to xij squared over xi squared xj squared. Okay, so this you can check as an exercise. And from the way xij squared transforms, you see that all of these factors downstairs are going to drop out because all u and v have the same weight in all 4 points. Okay. So u and v are the so u and v are the only 2 independent crosshairs of 4 points, which is another way to say that there are 2 real numbers hidden in the conformal invariant information. What we said before, right? We said that we can put x2 to a 2-dimensional plane, and the coordinates of x2 in this 2-dimensional plane can be parametrized by u and v. In fact, we can just do it. So let's go to the configuration that we said before. So x1 is at 0, x2 is in some coordinates. Let's call them, let's use complex coordinates, z and z bar. So x2 is in a 2-dimensional plane. x3, actually, sorry, let's call it x and y. So x and y are the 2 coordinates. And let's say that z is x plus iy, and z bar is x minus iy. Then in this 2-dimensional plane, x3 is at 1, 0, and x4 is at infinity. So now if I plug this in to the definition of u and v, you'll find that u is just x squared plus y squared, because so x4 goes to infinity, this drops out, this distance is 1, and this is just distance of x2 from the origin, which is x squared plus y squared. So that's z and z times z bar. And v, well, x4 goes to infinity, so this cancels that. This is 1, and this is just the distance of x2 from point x3. So v becomes 1 minus x squared plus y squared, which is the distance between x2 and x3. And that's the same thing as 1 minus z bar. Okay? Any questions? All right, and now let's think about the 4-point function. The 4-point function is not quite invariant under these conformal transformations, but it should transform in the same way like a 2-point like two 2-point function, right? We know that 2-point function of 2 identical operators looks like that. We saw that again yesterday or the day before yesterday, I don't remember. It's 2 delta O. So we can write the 4-point function as a product of two two-point functions, and we can pick any pair, this one, or this one, whichever you want. So let's just let's pick the 1, 3, and 2, 4. So the four-point function necessarily looks like that, times a function which is invariant. So it's a function of only u and v, or if you wish, z and z bar. Okay. In other words, the ratio of the four-point function and two-point functions is conformal invariant, and therefore it's a function only of the conformal cross ratio of z and z bar. So in the rest of the lecture, we can just think about this, we can just consider this function of two variables. Sorry, x. So x and y are the, we made some movements with the 4 points, and we brought x1 to 0, x1, x3 to 1, x4 to infinity, and x2 to a two-dimensional plane. And x and y are the two coordinates of x2 in that plane. And we can also parameterize them by z and z bar. Okay, so maybe I should draw the picture. So here is x1 is at the origin. Then there's infinity, right? So this is x1, this is x3, this is x4, and then x2 is somewhere, well, at coordinates x and y is what we are calling x2. Yeah, any more questions? Mm-hmm.
The fact that this factorization of the four-point function equals to one functions appears on that way is related to the
Nothing really factorizes. I mean, it's just a trick, right? So the four-point function doesn't factorize because the four-point function contains this. So this doesn't factorize. I'm just saying if you take a ratio of a four-point function and two two-point functions built out of the two pairs of points, then the ratio has to be conformal invariant, because for each of these operators picks up the same factor under conformal. I mean the conformal transformation of each operator is kind of independent of all of the other operators. So their transformation cancels in the ratio of the four-point function and two-point function. Is that okay? You seem you either think it's trivial or that it's incomprehensible. So, right. Okay, maybe I should I should write the finite form of the transformation. Because up until now we have thought about the conformal generators as the algebra elements. So maybe it's useful to write how the scalar primary operators transform under finite conformal transformations. So imagine that we have some mapping from RD to RD, which is conformal. Then how does that operator transform? So let's start with some operator OI of x of scaling dimension delta I. Then what happens after a transformation? Well, so the new the way I always remember it is that the old operator, sorry, the new operator at the new transform point. So let's call this, I don't know, O prime. So this is the or tilde. This is the operator after the transformation. Is related to the operator before the transformation. right? So we have to take the conformal map, compute the Jacobian of first derivatives, and put it to power minus delta I over d. So the claim is that this single formula encapsulates all of the formulas for the infinitesimal generators that I wrote down before, like PAOX is DIOX, and so on, right? There, we did the same thing for D, K, and M. So if you take F to be infinitesimal, one of these four, then this formula agrees with the formulas that I gave you for the infinitesimal generators. Okay? Is it? Sorry, I don't know. SD? What's SD? Oh, sphere. Oh, okay. Yeah, sure. Yeah. To be more precise, it should be SD to SD because some of these are going to send infinity to 0. But yeah, if you want to be careful, you can say SD to SD. Yeah. Right. So now, what is the logic? Well, the logic is we want to show that this ratio. The only thing that I said so far, which was non-trivial, is that this ratio is invariant. Yeah, so the claim is that this ratio is invariant under all transformations of this form. So this star is that transformation, right? And the reason why it's invariant is that this factor depends only on x1. I mean, for the first operator, it depends on x1, for the second one on x2, and so on. So it just goes out, and it cancels between here and here, here and here, here and here, and here and here. Okay. All right, so the next order in business that we have to understand what kind of primary operators can appear in the OP, right? So now we want to write down a bootstrap equation for 4 identical scalars. So what kind of operators can appear in this OPE? Well, the first operator that certainly appears is the identity operator. So the identity operator, which is the only one that has delta equal to 0 and rho trivial, and the appearance of the identity operator is just the statement that the two operators have a non-zero 2-point function, right? So when the contribution of identity is just a number, and is the 2-point function of OI of OX1, OX2, plus non-identity primaries, or non-trivial primaries. And of course, this 2-point function is the one that we know. It's x minus y to the power 2 delta O. Right? How do we see this? Well, we just take the 2-point function of both. We just take the expectation value on both sides. Here we get expectation value like that. Here we just get a number. And here, expectation value of this is 0 because we saw that the 1-point function of all non-trivial primaries is 0. Yeah, so if we take two-point function both sides, we get two-point function like here, plus 0 from all other non-linear primaries. Okay, so that's the identity. And well, what other kinds of things can appear? Well, they are all the primaries that can have a non-vanishing three-point function with a pair of scalars. So we saw, for example, that certainly other scalars can appear because so the question that we are analyzing is the question for which let me just write it. Let's say delta tilde rho tilde. So for these are the two identical scalars, delta O, and we are asking for which delta tilde and rho tilde can we find a three-point function, a conformal event three-point function. And the answer, so the answer is not obvious, but the answer is that rho tilde has to be symmetric and traceless. But of any spin. Okay, let me give you a rough reason why that is. So let's write the OP. I mean, it's basically because we can contract the indices of this operator with the position vector x1 and x2. But the positions commute with each other, so the only way this can work is if the operator is itself symmetric. Right, so how would we write the OPE? Yeah, let's imagine the contribution of this symmetric traceless operator to this OPE. Well, there's going to be some three-point function. Let's say, well, let's imagine that this is again I and j. So we have C, I, j, k. And then we have a symmetric and traceless operator, OK. But it's symmetric and traceless, so it carries indices. It carries j vector indices, under which it's symmetric and traceless. Okay, I think I'm going to need more space. But these indices have to be contracted as something because there are no indices on the left-hand side. Right? So the way we can do it is to say x1, 2 to the a1, x1, 2 to the aj. I mean, I'm not changing anything. I'm just going to compactify the left-hand side a little bit. Oy x1, oj x2. Sorry. Okay. TimesCijk plus descendants. Yeah, so this equation may look a bit messy, but hopefully it's clear that we are focusing on a contribution to the OPE of a symmetric traceless operator of spin j. And the way it works, well, we have to contract the indices with something, and the only thing that we have available are the positions of the operators, because these operators don't carry any indices themselves. I mean, if the operators carried indices themselves, we could leave some free indices here, but they don't. So we have to contract with x, and because the x's commute with each other, the representation has to be symmetric. And symmetric representation is not irreducible, but you can decompose it into symmetric traceless one. So necessarily, everything is symmetric and traceless. Does that make sense?
But you can introduce a set of auxiliary vectors.
Yeah, there is a way to organize the. Yeah, you could ask. No, let me not go there. But yes, it's a bit. Yeah. Okay. And by the way, this in this case, this number n, so the number n for trivial, and symmetric traceless. So let me write a symmetric traceless as the Young tableau with j boxes. This is kind of the standard notation. So in this case, the number is 1. So there is always just a unique 3-point function between scalar, and symmetric traceless of any spin. So everything is very, very simple. Well, everything has to be irreducible, and the symmetric representation is not, I mean, symmetric tensor power of the fundamental representation is not irreducible, but it's a direct sum of symmetric and traceless ones. So I mean, it's symmetric, but you should really decompose it into. So what's the statement? So if you take, let V be the fundamental of SOD. So it's a d-dimensional representation, right? Of okay, the dimension is d. Then you can consider the J symmetric power of V, but this one is not irreducible, but it decomposes as a direct sum of the symmetric and traceless ones of spin J, J minus 2, J minus 4, and so on. Good? Yeah. I mean, of course, for SUN, the symmetric power is already irreducible, so you don't have to do that. But for SON, you have to do it. Okay, well, maybe let's take a 5-minute break now. Okay, very good. So where are we? We are talking about four-point function of identical scalars, and we want to understand its OPE and the corresponding bootstrap equation. So let me first say what the bootstrap equation is going to be. Oh, sorry. Mm-hmm. For what? For getting a number. Which number? What is the number that you're referring to? The 4-point function? This. Yeah. The right-hand side is the trivial representation. So it's the one-dimensional trivial representation of the conformal group. It's the same thing as C, right? It's a one-dimensional. So I'm making a statement about representation theory of the conformal group. And the question that we're asking is, what is a set of 3-point? When is a set of 3-point functions non-zero? Like, basically, what are 3-point functions? 3-point functions, 3-point structures are conformal invariant maps from tensor product of theory representations to the trivial representation. They form a vector space. And we are trying to understand the dimensionality of this vector space, because that's this number n, right? This n ijk is the dimensionality of the vector space. And in particular, what's important is when is this vector space not zero-dimensional? And the statement I was making without proof is that if I and j are scalars, then this vector space is zero-dimensional unless rho tilde is symmetric traceless. Yeah, the proof, well, this was like a bit of a sketch of a proof that in the OPE, if you put some operator here with some basically, if any of these representations of SOD are basically either symmetric or anti-symmetric, irreducible representation, you can always decompose. And if anything here was anti-symmetric, you contract it with the axis, you get 0, right? Because axes commute with each other. So that's kind of like a sketch of the proof. Okay, so for identical scalars, the bootstrap equation is just the statement that when you write down the 4-point function, then that 4-point function is permutation invariant under all permutations of the 4 points. Is permutation invariant under the axis. Well, let me not write that. And in particular, under switching x2 and x4, we should get the same. Well, okay, let me just write. Is the same thing as if we substitute x2 and x4, and so we should ask. Well, first of all, this prefactor, the pair of 2-point function doesn't change because x1, x3 is the same, x2, x4 doesn't change. This is why I chose to take out x1, 3, 2, 4 rather than something else, because then it doesn't change. But the cross ratios change, and they change basically u goes to v and v goes to u. Okay, they're no longer here, but you should look into your notes and you see that u changes into v, which in the language of z and z bar is the statement that z goes to 1 minus z and z bar goes to 1 minus z bar. So since this doesn't change and 1 minus z goes to 1 minus z, the bootstrap equation or crossing equation, the crossing equation in this case is just the statement that g z z bar is equal to g 1 minus z 1 minus z bar. Okay, so that's the equation. So it's just some function which is symmetric under this transformation. Okay, maybe let me continue over here. And the statements that we are making about the OPE just now translate into statements about something like a Taylor expansion of this function g as z bar. Right, so let's consider this function g as z bar. Well, firstly, we know that there is identity. So there is going to be identity operator, which looks like the product of two 2-point functions. So let's just do it. So the identity would contribute x1 to the 2 delta phi, x1 2 to the 2 delta o. Let me just let's call it delta o2. So this is the pair of 2-point functions, right? But we are dividing it by x1 3, x2 4. So this is just the contribution of the identity operator, and you can see it. You can nicely write it as in terms of the cross ratios as just 1 over u to the delta phi, which is the same thing as 1 over delta o z bar to the delta o. Okay, so and now we have all of the other operators. The other primaries, which we have, well, more or less established with a bit of hand waving that they have to be symmetric and traceless. So let's write it as the infinite sum. Now I'm going to write it from 1 because m equals 0 for me is the identity. So it's some sum over many operators. And here is the 3-point function of C, O, and well, I'm going to call it m squared times a conformal block. which depends on this, the dimension and spin of the mth operator. It depends on this scaling dimension, delta O, and it depends on Z and Z bar. So let me just make this nicer. Just put like a substitution here. Put it as it should look like. So this is the full result. Okay, and this is the conformal block, which in principle can be determined using the algorithm that we have talked about yesterday by fixing all the terms in the OP and so on. But now you have to do it for general J. What we were doing yesterday was just for J equal to 0. Okay, so G is some special function, and there are various ways of determining it. Nice closed formulas, so there are kind of nice closed formulas. For G exist in even dimensions. But this doesn't really stop people from doing the bootstrap in odd dimensions, because you can still write various power series expansions of these conformal blocks, which work very well. Well, yes, yeah. In 1D it's very simple, but I kind of wanted to avoid talking about 1D in this card because it's a little bit of a degenerate case. So, yeah. Mm-hmm. These, yeah. So this OM is is symmetric traceless. So otherwise the C is 0. So yeah, exactly. Yeah, in principle, you're summing over all operators in the theory, all primary operators, but only the symmetric traceless ones contribute. Yeah.
What happens if you exchange x2 with x1 or x3?
If I exchange what, x2 with x4? Okay,
x1.
Well, you're just going to get the same equation under some change of variables, right? So so there is the group S4, the symmetric group on 4 letters acting on the 4 points, and the cross ratios U and V are fixed under a subgroup of degree of order 4. It's called the Klein 4 group, which just consists of the pairs of transpositions. So it's generated by this. So the cross ratios transform under the quotient. So this is a normal subgroup of S4, and their quotient is S3. Yeah, and so S3 naturally acts on the space of cross ratios, but basically Z goes to 1 minus Z, to Z over Z minus 1, and well, there's a few other combinations. Basically, these two things generate S3, right? They are the two transpositions. So this is the transposition 2-3, sorry, 2-4. This is the transposition 1-2, and these generate S3. But you will never get any new information if you just impose this for all Z and Z bar. That's all the information that there is in the crossing equation. it was under some change of variables. Okay, so I will not tell you how to derive these conformal blocks, but I'll give you some formulas, and maybe I can make some comments. So in 4 dimensions, there is a very nice closed formula for these conformal blocks, which takes the following form. So this delta, the conformal block for the exchange of symmetric traceless operators as a function of z and z bar looks as follows. So it's z bar to the power minus delta O. So this is what we will have for the identity operator. But for a general non-identity operator, there's some additional, not too complicated function of z and z bar. Okay, I think I'll have to start on the next line. That's right, so in principle, if you were to carry through the algorithm of determining the entire OPE contribution of a symmetric representation, you will arrive at this formula. So the conformal block is some power law out front times a special function of z and z bar, which kind of almost factorizes into function of z bar. It doesn't factorize essentially because of this factor here, and here k is a special function which is a hypergeometric. So the first time you see these hypergeometric functions, they look kind of scary, but if you work on conformal filter, you'll learn to love these functions eventually. But the way to think about them is they're basically a glorified power law. The important factor is this z to the h. In conformal filter, everything is some kind of power law. So if you only had the primary operator, you would basically just have this power law. And this 2f1 just captures the contribution of all of the descendants to it. So it's just some extra decoration on the power law. Okay, so this is so what's the bootstrap now? The bootstrap is the idea that if I write this function as a sum over conformal blocks, it's not obviously symmetric under z goes to 1 minus z, right? Because these functions are not at all symmetric under z goes to 1 minus z. So that equation is a constraint. The symmetry, let me just repeat it. Is a constraint, have a non-trivial infinite set of constraints on the set delta m jm and these numbers that I was calling COOM squared. Right? If you just pick some random collections of delta mjm and random collection of COM, there is no way in hell that symmetry will be true. So now let's start actually using this equation to prove some properties of CFTs. The first claim is that COOM squared is non-zero for infinitely many m. In other words, it was justified to write this as an infinite sum. There really have to be infinitely many terms here, otherwise you will not solve the equation. This is something that came up in the Q&A yesterday, but I only sketched the idea. Well, what's the idea of the proof? Is to take z bar. So for now, we can think of z and z bar as complex conjugates of each other. But so let's say that z to 1, which also implies z bar goes to 1 if they're complex conjugates in the bootstrap equation. So let's think about the right hand side. Right-hand side is 1 minus z bar as z goes to 1. Okay, so that's over there. Oh, there's a pointer. Nice. Okay, so what happens? So there's this factor, and this factor is some singular power law. Yeah. Right, so I claim that everything else in this sum is subleading compared to the identity contribution. And oh, I can keep using the pointer. Excellent. The reason this is the case is that at small, so this delta j, 1 minus z bar, as z goes to 1, goes like 1 minus z to the to power delta minus j over 2 minus delta o. I think delta plus j over 2. So this is just something you can check from those formulas. Basically, everything is a power law, and the power law is decaying. Sorry, the power law is diverging slower than the one of identity because of these extra factors. And as we saw, delta has to be greater than d minus 2 plus j. So in 4 dimensions, this is j plus 2. Right? So in delta minus j is always greater than 2. So this is always a positive number. So this power law is weaker, diverging in a weaker way than the one from identity. Okay, so this term dominates. From the point of view of the right-hand side. Now, from the point of view of the left-hand side, we need to take the z goes to 1 limit of these special functions. And you can check in Mathematica that they diverge slower. So this goes like some logarithm. Okay, so it only goes like a logarithm of z, basically, as z goes to 1. I could show you, I could just implement this Mathematica and show you, but I think I don't really want to do it in the interest of time. So you can check it yourself. I have the formula over there. So if the sum was finite, we would get contradiction, right? Because a sum over finitely many terms that only go like a log can never equal to something that diverges like a power. The divergence is stronger on the right-hand side. So if the sum was finite, you would get a contradiction. So the sum has to be infinite. And then so what happens? As you take z closer and closer to 1, the sum on the left is dominated by kind of heavier and heavier operators with higher and higher energy, and the convergence is not uniform. So you can reproduce, and you do reproduce this power. Okay. So there are infinitely many primaries. That's what I was promising you several times already. Okay, hooray, we have a proof. Well, the way I phrase it is just for the equal to 4, but it's completely general. It's true in any. I mean, the properties of conformal blocks that I'm using are true in any D, also in 2D. So, yeah. Mm-hmm. Yes, yeah. I'm imposing unitarity, and then, well, sorry. Am I actually imposing unitarity? In this argument, I'm not really imposing unitarity, I think, because, well, at least the only thing that I'm using is that identity dominates on the right-hand side. That I need. Oh yes, yeah, that's true. I use the unitary bound over here. That's true. Yeah. So with yeah. True. Yes, there are infinite exchange operators in the OPE, and therefore you need infinite operators in your theory. Yeah, but the OP is not a tensor product. I mean, tensor product is just representation theory. OP is physics. So the question is, what are in physics? Do they have to be infinite many operators or not? Okay, I don't know if I'm answering your question, but don't think of the OP as a tensor product of representation. I mean, the representation theory constrains the form of the OPE, but the fact there are infinitely many terms in the OPE has nothing to do with decomposing tensor product representation into a direct sum. It's completely unrelated. It's yeah. It's physics, right? There is a mathematical statement. Take two representations, decompose it into a direct sum. You get some answer which doesn't depend on which CFT you are in. Like, it's just a statement about representations. But then there is a statement about CFTs. So if you take two operators in a sum conformal field theory, their OP is going to contain some particular set of representations which have nothing to do with doing any tensor product. And okay, that's true. The OP is constrained by representation theory arguments, as I showed. But you see, there's a difference between kind of kinematics and dynamics. Tensor product is kinematics and dynamics. It's theory. One is theory independent. The other one is theory dependent. Okay, so maybe the final thing I want to do this lecture before we go to 2D in the final lecture is to give you an example of an exact solution of the bootstrap equation, which arguably is quite simple, which is the free theory. Yeah, so how does all of this work in the free theory? Okay, so we are still in D equal 4. And let's consider the 4-point function of the free field. So now O became phi, and as you know, delta phi is d minus 2 over 2, which is 1 in 4 dimensions. So actually, you can also just write down this 4-point function. So what is this 4-point function? Well, it's the sum of Wick contractions of which there are 3. Hopefully it's clear what I mean by this notation. So this means that this function g of z bar, so now I want to divide this by this, right, 1, 3, 2, 4. So if I do it here, I'm going to get the identity that we already saw. That's just this one. Then here I divide this by itself, so I just get 1. And here I get v to the minus delta phi, so that's the same thing as 1 minus z bar to the power minus delta phi. But remember that delta phi is actually 1, so I can simplify it and write it as minus 1. Okay, so this is the answer for the 4-point function in a free scalar, and it's one of the few examples where you can actually write down the full 4-point function as a function of z and z bar. And happily, it is indeed symmetric under z goes to 1 minus z and z bar goes to 1 minus z bar, because this term is invariant and these two terms are exchanged under that permutation. Okay. Now, what about the OPE? So now we want to take this 4-point function and write it as a sum over conformal blocks. So there will be the conformal block of the identity, which is already the first term. And then there should be some infinite sum over the primaries, which appear in the OPE, of their 3-point functions squared times the conformal block of the scaling dimension and spin of z and z bar. And here delta O is 1. Okay, so what remains to determine is what is the set of delta MJM and what are the corresponding structure constants. And here it's not very hard to actually figure out. There are 2 different ways of doing it. One is to think about a free field and just consider this OPE and think what should be on the right-hand side. And the other one is just to take this function and decompose it into conformal blocks. Right? And like we said, the conformal block is basically a power law. So this decomposition is kind of like Taylor series decomposition of the function. But before we do it, let's think a little bit about what we expect. So there should be the identity. Well, in a free field, we have the luxury of being able to do normal ordered products in a nice way. So this is an exact identity. Right? This is more or less the definition of the normal ordered product. Is the product minus the 2-point function Yes. Okay. Yeah. Yes. Oh, yeah. Over all primaries. There are infinite limit primaries. Yes. Always. Are you thinking about 2D CFT? Yeah. So in a 2D CFT, as we'll see tomorrow, there is a different notion of a primary, which is called a Virasor primary. And there are special 2D theories where there could be finite limit of Virasor primaries. So in the equal, let me just quickly say, in the equal 2, there are bigger representations, which are representations of Virasoro, which are labeled by the same, basically the same numbers. But these representations are not irreducible under the group that we are using. We're using a smaller group, the global conformal group. And if you decompose these bigger representations into irreps of the group that we are using, you'll find infinitely many terms. So there is some infinite sum over the things that I'm calling R. So already from in the two-dimensional Ising model, already from the identity Virasor representation, you get infinitely many primaries in the sense that I'm saying. So there's no contradiction between what I'm saying and what's happening in 2D. But in fact, for generic 2D CFTs, there are infinitely many even of these. So when C is greater than 1, you need infinitely many of these from Cardis formula. So it's very special that you ever get finitely many things, but that's when you can solve your theory. Yeah, so everything, I think more or less everything that I said also applies in 2D. There are some small asterisk with this unitarity bound, because then, d is equal to 2, delta can be equal to j, but let's not forget. Okay, so that OPE, well, let's look at the second term. So the second term is equal to that sum over m, right? So is the contribution of all the non-identity operators. If you want, you can just do a Taylor series. Okay. Yeah. One thing that I learned is the importance of Blackboard space management, or I mean, I should say I haven't learned, but that's yeah. This is just a Taylor series, so you can see the only things that can appear are quadratic in phi. That's very special for the free field. But this operator is not a primary, so this sum kind of reorganizes in a rather complicated way into a sum over primaries. So what are the primaries in this sum? Well, at n equals 0, there's a primary, which is just the square normal ordered product of the square. So that's a primary. It has dimension 2 and spin 0. Okay. At n equals 1, it turns out there is no primary because there is only one operator, right? And this operator looks like that. And this is actually a descendant of this primary. It's right. So at n equals 1, there is no primary. At n equals 2, there is a descendant, which is the level 2 descendant of this one. So that one would look like a1, a2, phi. So we need to take two derivatives of this. So you get something like plus. Right, so this one is a descendant. But it turns out that there is a primary, which is the same thing with a minus sign, right? So now the space is kind of two-dimensional. So if you put a minus sign here, then it's a primary. It's a primary of dimension delta. We have two phi's and two derivatives, so delta is 4. And we have two indices, so spin is 2. And it turns out if you keep going, you can convince yourself. I think this is probably too hard of an exercise, but you can think about it, is that the set of primaries in the OPE of two phi's, they look more or less like this. So there's phi, j derivatives, and phi, where j is 0, 2, so all the even integers. And this derivative acts on the left or on the right with a different sign. So this is supposed to be, this notation is supposed to be delta AB minus a delta B. Okay? And this primary has dimension 2 plus j and spin j. So there are indeed infinitely many of them. But now we should be able to check whether this is true by looking at the bootstrapping at the OP of the 4-point function. So let me just show you quickly in Mathematica, and then we'll go for lunch. Unless, maybe before that, are there any questions about what I said? Well, at j equals 1, there's only one thing you can write down, and it's a descendant, right? It's a descendant, but from the point of view of this formula, if you do this odd number of times, the two terms will cancel each other out, so, right? Because in our case, a is equal to b is basically equal to phi, right? So this minus that odd number of times is 0. So this only works for so j is even. This is related to the symmetry under switching 1 and 2, that you only get even j. It's like a selection rule. Okay, any more questions before? Yes. Ah, yes, sorry. Okay, let me do it. Any more questions? Okay. Feel free to follow along on your laptop if you have it with you, but no pressure. Okay, so what we have so far of the free scalar 4-point function. Okay, I have some window which obstructing my view. Point function. Okay, so we have the 4-point function, which is this graphic G. Maybe let me make it even bigger. Okay, so we said that this one looks like z bar, so zb is z bar, then plus 1 plus that, 1 minus z, 1 minus z bar. So that's the 4-point function. Then we wanted to define the conformal block. So the conformal block for some external delta O and exchanged scaling dimension delta and spin j is some function of z bar, which we said was z bar to the minus delta O. Then there was z bar over z bar minus z. Then we had a special function, which I think I already defined before, so let me just forget it. So I'm just writing the formula that I wrote down earlier on the board. Sorry, this shouldn't be z bar, but just z. It's symmetric, and the whole thing should be symmetric under switching z and z bar because of reality. And then this k is the special function, which is basically a power law. So it's like z to the h. For those of you who know 2D CFT, this h is like the conformal, becomes the holomorphic conformal dimension in 2 dimensions. But here the power law is decorated by this extra hypergeometric. And I hope I didn't make any mistake. It's probably okay. Okay, so first of all, let's just check something simple. So we are doing, so our delta O is equal to 1. So let me just put 1 as the first entry. Actually, let's call it conformal block, so it's totally clear. So conformal block is what I was calling G before on the blackboard. So 0, 0 is the identity, right? It's delta equals 0, J equals 0. So let's just check that it makes sense. Yeah, it's 1 over z bar. That's what it should be. So that means that we can let's just subtract it. Okay, and we still get something non-zero. This should be the sum over all of the phi squared type primaries. And the way we can analyze it is by taking the small z bar limit. So let's go to polar coordinates. So this is the z in polar coordinates, and this is z bar in polar coordinates. It's just the complex conjugate. So r is some real number, whichever you're going to take to 0. And let's look at what this what it looks like at small r. Okay, it's 2. And what is this 2? The 2 is like the non-singular term if we subtract identity. So it's the phi squared operator. Right? This 2 is the phi squared operator, which is the conformal block of dimension 2 and spin 0. So let's put dimension 2 spin 0 plus. So this tells us that this coefficient is 2. So in other words, we learned without doing much of a calculation that, okay, let me just write the formula. So this 4-point function, what we expect is this z bar to the minus 1 plus sum over spins, over even spins, so 0, 2, 4, and so on, of c, now it's some cj squared, times the conformal block of dimension j plus 2, j, z bar, 1. And what we have learned so far is that c0 squared is 2. I mean, it's something we could have in principle done by actual calculation, by taking this primary, normalizing it, so this primary normalizing it and computing the 3-point function and squaring it. But here we kind of get it with very little work just by decomposing the 4-point function into conformal blocks. But now we can keep going. If you go, so first of all, going to the contribution of an operator of dimension delta goes like r to the delta, or r to the delta minus 2 in this case. So this tells us there are no new operators of dimension 3. But now you see that there is there is an operator of dimension 4 and spin 2, because this kind of looks like the dependence on theta more or less tells you the spin, so we can so I believe this should be like, so we can put some unknown number, which is the c squared of the operator of spin 2, which has dimension 4 and spin 2, and this tells us that the c squared needs to be 1/3. Okay, and so on. So in this way, you can kind of keep going, and well, let's do it. Let's just do it one more time. Okay, so plus c squared of spin 4, conformal block of dimension 6 spin. Okay, so this tells us that c squared at 4 is 1/35. And okay, if I remember well, the formula for c squared of the one spin j. Okay, I did this exercise a few times in my life, so I happen to remember that it's this. We could have done it. We could have just guessed it by going to higher orders. You see that, for example, c squared of spin 0 is indeed 2, of spin 2 is indeed 1/3, for spin 4 is 1/35. So that seems to work. So let's just check it. Okay, so we can do like a sum of the c squared. So what are we doing? We are summing c squared and conformal block of dimension j plus 2 and j, spin j, from 0 to some j max. So we'll just truncate it for now. And we can put j max to be, I don't know, 10, 20. Okay, so this gives you some kind of horrible looking sum. And, well, does it agree with the 4-point function? Okay, what we are supposed to do is to expand. And we can expand to, I suppose, to the order j max.